Here we are inside Working Model once again. I'm going to click on New Document here. Now, if you haven't already watched the video on creating a Whitworth mechanism, I suggest that you do so if you're interested in learning about what we have in the different tool palettes on the side. So let's go ahead and let's get started by taking a look at our DXF geometry we have for this example. I'm running SOLIDWORKS in this particular case. It's not necessary that I run SOLIDWORKS, as we can get DXF geometry from any CAD system. What is important is that if we wish to create any constraints on this geometry once it's inside Working Model, that we add points wherever we wish to add a constraint. So you can see that I've added these point elements here, and when we get into Working Model, we're going to do an extra step with those to make sure that they come through successfully. So we can save the DXF. I've already done that, so I'm going to toggle over to Working Model. And before we read in the DXF geometry, it's important that we set the units so they coincide with the units that were drawn with the SOLIDWORKS drawing. So we can click on View, Numbers and Units, and we can set the units here. Again, we explained a lot of these features as we went through them in the previous video, but we'll choose SI degrees, and then we'll change the distance to millimeters. Click OK, and now we'll go ahead and we'll read in the geometry. So we'll import. We have that DXF file that I saved previously, and there's our geometry. So the first thing we need to do is we need to attach these points to their respective bodies. By default, they come in attached to the background, and therefore they won't allow us to select them to define constraints. So we'll go ahead and we'll just use a little mouse selection window, and I'll select both the point and the cam at the same time here. Choose Object, Attach to Body, and then I'll click on the follower, hold the Shift key, select that point. Let's try and zoom in a little bit. Maybe grab a selection window, it's easier to pick it. Sometimes bodies can be overlaid, or they can be brought forward or sent backward. Similar to what you do in a Word document, you have the ability here to move objects forward and backward. So we have the point, Shift key, select the body, and we'll attach that point to that body. Same for this point here and the valve. And then finally for this point down here and the valve guide. Okay, so those points are attached. Now right now this model is not constrained by anything, so if we ran the simulation it would simply fall with gravity. So we'll get started by adding our constraints in here, and I'll just click on the motor tool, and then I'll hover the mouse over that snap point and I'll click, and now we have a motor defined for that. While we're here, let's go ahead and let's modify the properties for that motor. By default, it's turning at the speed here. Let's change it to 360 degrees per second. Next, we'll add a constraint or a pin joint for the rocker. Next, we're going to add a slot joint for the valve to the valve guide. And in order to do that, we're going to use the point elements that we also discussed in the previous video in creating a Whitworth mechanism. We'll go ahead and we'll start by clicking on the square point. I want a square point and a slot so that when I join them, it will create a keyed slot. That's going to be different from a pin slot joint in terms of the degrees of freedom. So I'll just zoom in there a little bit. I'll click that point, and I've got that. So I'm going to double click that point while I'm here, and I'm going to modify the angle of it to -65. That coincides with the angle at which this is turned right here. So I knew that in advance, and I need to make sure that the point is aligned in that direction. Okay, and now we'll go ahead and we'll add a slot, and I will click on, I don't have to use that point. I can hover down here over the snap point. I'll save this point right here for when we attach a spring between those two. So I'll hover over there and I'll click, and it doesn't know that this body is rotated, so I simply have to tell it to rotate the slot 65 or -65 degrees. Now that the slot is selected, I can hold the Shift key. I can select the square point right there. Notice how the join feature woke up. Now I can click on join, and those two should be joined together. And before I drag them to verify that they are connected, I need to add an anchor to the valve guide here so that it doesn't move around. Now if I click, hold, and drag, that looks good. So it's good to check your connections as you build them to make sure that you have the proper degrees of freedom. This part isn't flopping all over in space for some reason. And we'll undo that movement. Now we'll go ahead and we'll add a spring element in between the valve and the valve guide. And you can envision the spring resting on this bottom surface here, so that's why I'm using the midpoint of what that circular surface would be in 3 dimensions. Okay, so we have a spring, and like we did in the previous video, we created slider input controls to help us to be able to adjust parameters in real time during or before a simulation. So with the spring selected, we'll click on Define, New Control, Spring Constant. And now we have a spring constant that we can vary using the slider control right here. I'm going to double click the slider and I'll set the lower and upper bounds for it. And we'll say it has a maximum of, say, 50 newtons per millimeter. And then for the increments, we'll choose 49, which will give us 1 newton per millimeter increments for every increment of the slider. Okay, so now if I move this, okay, didn't exactly give us 1 millimeter increments. I think because I had one, I need to include, that was supposed to be 49. Let's make that 49 and let's try that again. There, that looks better. So we have some arbitrary spring stiffness defined. And just for kicks, let's go ahead and run this simulation. Before we do it, let's change the default for the step size so that it is something smaller, maybe 0.002. So we capture several frames per second. It all depends on what the speed of the model is going to be as well. So if you have real high speeds, you might need a lot of frames per second. Then I'll change the integrator error to 0.001. I'm going to tighten that up a little bit because we're going to be defining contacts between a few of these bodies in here. And then also under more choices, I'm going to adjust the overlay error to be 0.1, or overlap error, excuse me. Select OK. And let's go ahead and let's run this. And by default, it's colliding already between those two surfaces. If you'll notice, we didn't define any collision between those two. But by default, working model is set to have bodies collide if we don't specify. So we can always uncheck and then specify collisions where we want. We don't have to let the program do it. Okay, but in this case it looks pretty good. So let's go ahead and just create a couple meters in here, and maybe we'll click on the rocker arm, hold the shift key down, select the cam, and we'll choose measure contact force. I'll just move that meter by that collision area, and then maybe we'll right click on the spring, measure the spring tension. Okay. And then before I run this, I'm also going to select all 3 of these bodies. I'll hold down my shift key and then I'll right mouse click and choose properties here. And to start with, I'm going to define the elastic coefficient as 0.01. 0.5 is rather elastic for, say, steel on steel, so let's do something that's a little more representative of something stiffer. Okay. Now we'll go ahead and we'll run the simulation. Okay, and we can see we're getting some feedback, and I can see that I don't have much preload pushing back, so this force eventually goes to 0. So we might want to add a little preload into the spring. If I just double click the spring, it shows me the current length. That's the current distance between these points. But I can specify that, for example, I wish the free length to be 48 millimeters. So the difference between the length and the current length multiplied by the stiffness is going to give me my preload force. So let's go ahead and run this. Now you can see we have a constant preload on here. And you see these numbers cycling. That's simply numerical error. For the most part, it looks like it's going between 359 and 360 for the force. We could simply modify some of the accuracy settings to smooth that out. That looks pretty good there. Let's go ahead and let's turn on graphical vectors, which is very useful, like we explained in the previous video, for identifying, say, load case conditions or a free body state of the part, for example. So I'll click on this rocker, I'll right mouse click, that is, choose vectors, contact force, and we'll go ahead and run the simulation. You can see we have these vectors that are showing, and I can also tone down the length of those vectors by going to the vector lengths right here, maybe add another 0. We'll see how that looks. Let's try that one more time. Maybe add one more 0 for the scaling. And looks like we'd have to come down a little bit more. We're getting there. So you can see that we can create these vectors here, and very useful, showing us what the forces are and things like that. So as we run this, we see these values changing. Okay. Now, like we talked about in the other video, we can do other things in here and begin to add complexity to the model. So for example, if I wanted to study the torque on this motor, and I can create a measure for the transmitted torque. And let's just expand that to a graphical form, and let's bring the corner out a little bit. Now I can run this simulation like it is right now. I do have a little bit of noise in there, but you can see the clear trend once it starts to simulate. But I can stop this and I can retain these meter values. So now I can add something like friction on this slot, for example. I'll go ahead and do that, or that pin, and it's going to create these two sliders. So working model doesn't really know the size of the geometry. It just sees a theoretically perfect constraint. So I can tell it what the radius is and the friction coefficient, because the friction torque on this is going to be dependent on the radius of the pin. So I'd want to specify some values in here for something like that. Okay, but when I rerun this simulation now, I get a new torque profile over the old one, and still a little noisy there. I think what I might do in here is I might go in for now and just go into the properties and turn friction off or set it to 0. Let's work on erasing that, and we'll go ahead and run it again. Okay, that looks a lot smoother. Okay, so now we can change these values in real time, and we can't see much of a difference on there, and I'm guessing because our pin radius is not large enough. Let's change it to something like 20 millimeters. Okay, and now if we go ahead and run this, we can see quite a bit of a difference now. Okay, so being able to overlay these curves and compare the results is very helpful. Maybe we change this spring tension right here, and we can see what that does to the results. So very easy to set up these models, very quick to analyze them, very powerful, a lot of capability in Working Model 2D. The other thing I'd like to mention is that Working Model can be linked up with MATLAB and Excel. So control systems, for example, can be simulated along with the dynamic motion model. With Excel, you can exchange information in real time. Maybe there's formulas set up in Excel. Maybe there's a table of data that you're using to interpolate with, maybe drive a motor. And we can also read in table data directly using a feature that allows you to assign, say, velocity versus time to a rotational motor. So we can drive the mechanism using data, for example, that may have been measured in the physical world.